Welcome. We are looking at the solution to the diffusion equation, and we derived the expressions using explicit and implicit discretization schemes. We haven't talked about exactly how the boundary conditions are implemented. We will look into the details today, and we also want to write scripts in Octave to solve for these equations. So, the equation that we are trying to solve is the diffusion equation. So, it is dou C by dou T is equal to d del squared C by del x squared. This is the equation that we are trying to solve. And the discretized version looks like this. So, C at any point I t plus delta t is equal to C at any point I t plus d dt by dx squared. I probably use delta t and delta x. So, let me use delta t delta x, and then C I minus 1 t minus 2 C I t plus C I plus 1 t. So, I am going to call this d delta t by delta x squared as some alpha. So, it becomes C I t plus delta t is equal to C I t into 1 minus 2 alpha plus alpha times C I minus 1 t plus C I plus 1 t. Now, let me consider a scenario in which, of course, it is one dimensional diffusion, which means there is diffusion barrier on this side. So, diffusion can take place only along the x direction. And let me assume that at this point where x equal to 0, the composition takes a value of 1. Okay. So, this is all normalized. So, this is going to take a value of 1. Everywhere else at the beginning, the composition is going to be 0. And as time proceeds, what happens is the thing that we are looking at. So, initial profile is very clear, it is 1 and then it goes to 0 everywhere. This is the at time t equal to 0, this is C as a function of x, right. So, this is the initial condition, and we have one boundary condition. This end is always kept at 1. The other end, we need to decide what is the boundary condition going to be. So, I am going to keep the boundary condition that there is no flux at this boundary. In other words, I am going to consider the boundary condition as follows: dou C by dou x at this point L is equal to 0. What is the implication of this for our discretization scheme is what we need to look at, and what is the implication of this for our scheme is something that we need to look at. So, let us take a closer look at the boundary condition. So, I have this boundary condition at one end, at the left end, where we have the first node point, the composition is always kept at 1, right. C where I equal to 1 is for all times equal to 1, right. That means, this is not changing with time. So, I do not need to solve for this equation at all. The solution this point, when I have this expression which says C I t plus delta t is equal to C I t plus something something, I do not need to consider the case I equal to 1, because I equal to 1 there is nothing is happening. So, it always remains at 1. Now, when I is equal to n, that is the point where x equal to L, we are assuming that dou C by dou x at this L equal to 0. Okay. Now, what does that imply in our case is what we want to know, because C I t plus delta t is C I t into 1 minus 2 alpha plus alpha times C I minus 1 t plus C I plus 1 t, right. This is the expression that we have. Now, when I am at this point, right, this is x equal to 0, this is x equal to L, and for this point when I becomes n. So, I equal to n here, I equal to 1 here, and then there are these delta x changes. When I am at this point, I know that for this I there is an I minus 1th point. So, this is not a problem, but I need to know what I plus 1 is. That is a ghost point here, a point which lies outside of our domain here. The way to calculate that is that there is also this discretization for dou c by dou x, which says that c I plus 1 minus c I minus 1 by 2 delta x. This is also dou c by dou x at the point I. Okay, so, this discretization is also there, this is the central difference discretization. So, this discretization if I use, and because it at L this is equal to 0, that is L is I equal to n, right, that is the point, this is x equal to L. At this point this is 0, this condition is satisfied if I take C I minus 1 to be equal to C I plus 1. In other words, for the nth point, this is the last point, I am going to assume that C I minus 1 and C I plus 1 are the same. So, that becomes 2 alpha C I minus 1 t. So, for just for this point, it becomes C I t plus delta t is nothing but C I t 1 minus 2 alpha plus 2 alpha C I minus 1 t, because I minus 1 is something that is available, I plus 1 I do not know. I replace the I plus 1 in terms of I minus 1 using the given boundary condition. So, this is what I am going to do first, and we are going to see how the solution evolves. It is possible to look at in this case also how the solution evolves in interactive mode by writing the code, but it is far more easier if we do it in script mode, because later when we are going to change this boundary condition, you can take the same script, you can change only things corresponding to the boundary condition, and you can save it as a new script file and you can run it. So, that is the reason why I am going to write a script in Octave for solving using this explicit discretization scheme with the boundary condition that at one end the composition is always stays at 1 and at the other end the flux is 0. Okay. No atom when it reaches that end can escape. So, when it reaches that end, it is just stuck there. So, that point the concentration as time goes is going to build up, more and more atoms will come from one side and it will reach that point, and so you can't go beyond that point. So, it is going to increase the concentration at that point, which is the solution which we will see later, which is what we expect to get. And so, let us write a script which will do this computation. Okay. So, this is explicit method, that is all the right hand side of the discretization we took at the same time t, which is the current time using which we are getting the future time, and we are having no flux boundary condition at the right end. Left end is Dirichlet, right hand is Neumann. Okay. So, let us do that as usual. We go to the computer, open a terminal, okay, and then I am going to the directory which I am going to write the script in, and I am going to invoke Octave from that. Okay. So, Octave is there, and if I now write the script, I can come here and source the script, I will get the solution. Now, for writing the script, I am going to use this program called gedit. You can use any text editor, a simple text editor, notepad kind of things are okay, but you should not use Word kind of editors, because they put lots of hidden characters which interfere with your code. So, let us save this file as, I am going to save it in the same directory in which I have invoked Octave, that is facefill MOOC directory. I am going to call this program as explicit no flux 1D diff.oct. Okay. So, it is a good idea to name the files very clearly, so that by looking at the file name you know what the script is going to do. So, first thing we do, it is always a good idea to, so let us put clear figure and clear all. Okay. So, we have cleared all the variables or parameters that Octave might have in its memory. We have also cleared the figure window, so it is a clean slate from which it is going to start the computations. Now, let us define this variable delta t and delta x. So, this is how we do. So, let me call it as del t is equal to some value. So, let me take a value of 0.1. Please remember, even though in the equation I call them as dou c by dou t and del squared c by del x squared, as I explained, we assume that all these quantities are non-dimensional. Okay. So, delta t, when I say 0.1, it is in some non-dimensional units. It does not have any unit. It is not second, it is not hour, it is not minute, it is not day, it is non-dimensional, it is just a number. Okay. So, same is true for delta x also. Del x is equal to, let me take in units of some 0.5. Okay. Now, I am going to define, and the d, the diffusivity we need to know. Let me define the diffusivity as 1, because this is non-dimensional. I have taken non-dimensional diffusivity of 1. So, we said that some quantity is alpha. So, let me call it as alpha. That was nothing but d into del t divided by del x into del x, right. So, this is dt by del x squared, which we defined as alpha. So, I want to now define the initial profile. What was the initial profile? So, it is a good idea to put some comments, and let me put the comments here. So, clean the figure and clear all data. So, that is what is being done here. Then define the parameters. So, that is what being done here. So, we have defined the parameters. Okay. So, now we are going to go and set the initial profile. Okay. So, initial profile requires, so I am going to take some C, and this is the way to define a vector. So, I am going to say zeros 101 comma 1. So, what does this mean? This means that it is going to define a variable called C, and it is a vector because it has 101 rows and 1 column, that is what 101 comma 1 means, and it is going to initialize this vector to have zeros in all the 101 rows. It is a column vector, and it is going to put zeros in all the rows of this column. Okay. So, zeros is a way of defining or initializing a vector to have 0 value, but we know that C of 1 is always 1, right. The rest of them remain at 0, but C of 1 is 1. So, this is the initial profile. Okay. Now, it is a good idea once we have done that to plot the initial profile. Okay. So, let me plot the initial profile. So, I am going to plot, it as C. Okay. So, I am going to plot it with in red color and with line, and then I am going to say that it should be labeled as initial profile. Okay. So, that is what this means. So, I am plotting C. So, C is 101 points. So, those are our node points, the 101, I equal to 1, I equal to 2, etcetera, I equal to 101, that is what this means. And at those values I have taken the C value to be something. So, this is the initial profile. I want to distinguish the initial profile from the other profiles that we are going to plot as the composition evolves. So, I am going to plot the initial profile as a line, that is what the dash indicates. It is a red line because the other ones will come in the color blue. We know by default it starts by plotting with blue color. So, red line will be the initial profile, the blue color will be the actual profile after some time and so on. And we are going to label the profile as initial profile. So, it will draw the red line and it will put a red line up there in the legend and say initial profile. So, people know which is the initial profile. Okay. So, that is what this one does, and then there are things that you can go do to the plot. Probably it is a good place to introduce some of them. You get what is known as the handle. Okay. Get handle. So, what is handle? So, I am going to say A x is equal to G C A So, this is getting handle for the access box. What is the purpose? So, if you say set Ax comma line width comma 2.0. So, what it will do is that it will make the box of the plot a little bit thicker. Okay. You can also make this other one. So, generally I like my plots to be square instead of rectangle. So, axis square will make the plot a square. Okay. So, so there are ways of changing things. So, you can change the box, the width of the line which makes up the plot box. I have made it thicker, and I have made the plot itself a square plot. Okay. Otherwise, it is generally rectangular. The width and the height are not the same in length. So, I have made it a square because I always feel that square plots look nice. Okay. So, you can do this kind of changing the properties of the plot that you are going to get. So, this is just to introduce you. You can go to Octave and look for help for getting handle on axis, and then or look at plot and then look at the subtopics and so on and so forth. Okay. Now, I am going to say, okay, so this is just that, and then hold the plot for future. Okay. So, I am going to say hold on. Okay. This plot will be kept, any other plot will be done on the same figure. So, we know what the initial profile looks like and what the profile looks like after some time. Now, I am going to introduce 3 loops. Okay. So, what are they for? So, we will look at, let me take for k is equal to 1:20. This loop is for plotting. Okay. So, there will be 20 figures that will be plotted. This outer loop is for plotting. Then the inner loop, so for j is equal to 1:500. So, the plot will be done once in every 500 steps, right. Delta t is 0.1 I think we took. So, 0.1 into 500 is like 50 time units once the plot will be made, and that is what will be plotted. So, that is why we have the other variable k. Now, of course, for I is equal to 2 to 100, because remember the first point we said is not in the equation at all, because it always stays at 1, and we have taken it to be 1. So, it will remain at 1 for all times, because we are not going to change it at all. Now, only up to 100 points, because 101th point the expression is slightly different. Okay. So, what we are going to do is that we are going to have an inner loop which evolves the composition values at points 2 to 100. 1 always remains at the value, 101 will be evolved outside of this loop, and once 500 such steps are taken, then the plot will be made, and then it will go back and make another 500 steps, and then plot will be made, and so on and so forth. So, that is why there are 3 loops. Okay. So, the outermost loop is just for plotting purposes. Okay. So, now what do I say? C of I is equal to C of I into 1 minus 2 into alpha plus alpha times C of I minus 1 plus C of I plus 1. Okay. So, this is the expression. I am going to end the for loop. Then I am going to say C of 101 is equal to the same expression, except that I am going to copy paste the same expression, and then I am going to say that it is 2 times alpha into C minus 1. There is no C plus 1 that is needed. Right. So, this is what we said happens because of the boundary condition, because of the no flux boundary condition. So, that is what I have implemented. So, remember what happens. So, it goes through this loop, then it does this for each j. So, 500 times it has to do this. So, let us end the j loop, right. So, this is for the I loop, so this is for the J loop, and after the J loop I actually want to plot the function, okay, and then I am going to end the K loop, and for this is for the K loop, right, and then okay, so this is the this part should be called evolve the composition and plot, okay, so that's what we have done here. Of course, it's always a good idea, so save figure, okay, this I haven't shown you earlier, so you make all these figures, they look nice on screen and you might want to keep a copy of the figure. So here is a way to save the figure in whatever format you want. I am going to show you EPS, encapsulated postscript format. It is also possible to save it in JPEG format, okay. So I am going to say print print minus device, which device it should plot, print to the encapsulated postscript color, okay. So I am going to save this figure as explicit no flux dot EPS, okay. So let us save this script, okay, let us run through the script once more. So we cleared everything, we determined the parameters, we decided what is the alpha, and we set up the initial profile, we plotted the initial profile, we made some small adjustments to the figure, we made it look nice, and then we said that every other figure now on should be plotted on the same plot, because we have the initial profile and we want to see how the time evolution is, and then we evolve the composition using this expression, which is the explicit expression, which is algebraic, which is the simplest way you can do, and then once you evolve some number of steps, you plot it, and then you go back and evolve for some more time, you plot it, and so on and so forth, and then finally you save the figure that is generated, okay. So we are going to do that. Now let us go here and run the program. So I have to say source explicit, okay. So the way to not type the entire file name is to type the first 2-3 letters and then press the tab key, and then Octave will fill it for you, because there are no other files which start with capital E and XP. On Linux machines, the capitals and small letters are distinguished. So EXP, if it sees and then there is no other file with this name, whatever is the only file name that is available, it will fill it for you. So we say source file name.oct, that is going to run the program, okay. So you can see that it first command was CLF, so it first put the figure, which is clean, there is nothing there, and now it is doing the computation. As it is doing the computation and completes it, it is going to come back and plot, but it completed, and there is some warning message which I do not think is important. I do not know if you are able to see clearly. So there is a red line, so it is 1 and then it drops to 0 and it remains at 0, but this line is merged with the x axis, that is why you are not seeing, and then you see the composition profile evolving. So initially this profile, so there is some concentration that is coming in and it is going here, it has not reached. So this is quite close to your error function kind of solution, the length is not reached, probably much earlier than that it will actually be a much better fit with error function. So we are going to do a tutorial to understand how the error function solution or where it is valid and things like that. But as you can see, as I mentioned in the last lecture, error function solution assumes that far away from this region, the composition always remains at Ci or the C initial that you started with. Obviously, in this case that is no longer true. You started with 0 and then this composition is building up. because of which these solutions are deviating from the error function solution. Okay. So, we are getting them numerically, they are certainly deviating from the error function solution. But the deviation is because we said that atoms can reach this point, but they are not supposed to escape here. So, the atoms come from all the way from here and then they get stuck here. Then what happens? At that point the composition keeps increasing. And you can also see another thing, that the gap between the points here is much larger, and then as time goes by it becomes smaller and smaller. That is because if you look at the concentration gradient, it goes from 1 to point some 7 and odd here. So, the overall concentration gradient which is driving the diffusion is lower as compared to here. For example, here the composition gradient was like about 1. Right, it was 1, it is 0. So, the composition gradient is about 1 minus 0 divided by whatever 80 space points, or much earlier it would have been some 20, 60, 80 whatever time points, space points. So, that is the gradient. So, the gradient is very large here. So, there will be more flux, because that is what fixed first law says, the flux is proportional to gradient, and as the gradient becomes smaller and smaller, the flux is also going to become smaller and smaller. So, finally, we expect that the composition becomes like 1 everywhere, right, that is the homogenization thing. And you can see that it also says that this is the initial profile, right. So, initial profile is noted here. Okay. So, that is the legend which says that the red line is basically the initial profile, and as time increases you see that the composition keeps changing, and finally, we expect it to become a uniform single composition of 1 everywhere. That is what we expect, and that is where this system is evolving. Okay. So, if you evolve for a few more like we plotted 20 times after every 500 steps, maybe you can plot after every 1000 steps and go to a much larger number of plots, then you will see that these are all getting crowded and then it becomes constant here. So, this is the one dimensional solution that we have obtained using the explicit method with one boundary condition being Dirichlet, the other boundary condition being Neumann. And the Neumann boundary condition said that the flux is actually 0. You can put some constant value for the flux, but that is not what we did. We said that the flux is 0, and this is the solution. So, and we have written the script to obtain the solution. So, that brings us to the end of this part of the lecture. Explicit, discretization, one dimensional diffusion equation, left boundary Neumann Dirichlet boundary condition, right boundary Neumann boundary condition we have solved. And the solution, as you can see, is very simple, and the advantage of using Octave is that as you are getting the solution, you can plot and you can look at the figures and you can actually understand what is happening, because the computation and the visualization are happening together. Okay. Of course, you can also see that it takes some amount of time to do the computation, because there are overheads that it is doing the computation, it is taking the values, it is plotting them. So, all this takes some time. So, even though it is Octave use is good for these kind of purposes, if you want to write any professional quality code using which you will generate results which are, for example, publishable, some new research that you are doing, then Octave is not very efficient. It can still do the job probably for you, but it is not very efficient. 1D and about 100 points, and you can see the kind of resource it requires, whereas a program which is written in C or Fortran will be much more efficient. Of course, the disadvantage there is that you have to write the data to a file and you have to invoke this plotting as a separate exercise. It is a post processing exercise that you need to do. But here initialization, running the code, post processing, everything is done in one go. So, it is great in terms of learning things, but once you know, probably for more involved computations, you may have to go to a programming language like C or Fortran. Okay. So, let us end this part of the lecture here. We will come back and try to look at solving the implicit scheme, because that involves a matrix operation. So, we have to pose the problem in terms of the matrix equation, and we have to solve the resulting set of matrix equation. So, we will do that in the next part of this lecture. Thank you.